It's like the diazonium of methylamine.
Okay, weak base equilibria, very similar, very analogous to weak acid equilibria. A lot of the same rules, same equations. They're going to seem very similar, just we're talking about bases instead of acids. That was a vocabulary we went over the other day. A lot of those terms might come up again, but really we're skipping over that. Just to recap the main key points from last lesson that are relevant to today. Well, we learned about something called the acidity constant. Guess what? We're going to learn about something called like the basicity constant, or the base K constant. Cool. KB, K sub B. Yeah, that's what we're going to learn about today. Okay, so what is Ka? It is the equilibrium constant for a reaction where a weak acid dissociates and reacts with water to produce two things: a conjugate base of that acid, and it's given the general general formula A minus, right? And H3O plus is produced, right? Hydronium. And we made an assumption that simplified our Ka expression, didn't we? What was the assumption we made here to simplify that equation? Yeah.
The concentration of H3O plus and the concentration of our acidic ion that's going to be the same.
Yeah, the conjugate base ion and the hydronium are present in equal concentrations. Not quite true, but we can make that assumption as long as we're not looking to report our numbers to like 7 or 8 sig figs. Because the amount of hydronium comes from two sources. The second source is the reaction of water with other water molecules, right? The dissociation of water reacting with itself or other water molecules. And that produces only a small amount of hydronium, so that's why we can pretend like it doesn't contribute to the concentration of hydronium. Cool. So we made that assumption. But the second assumption we can make also is that when we solve these equations, we can plug in the initial concentration of the weak acid in the problem, because that is an assumption. At equilibrium, that concentration has decreased, obviously. That weak acid is a reactant. Over time, it will have reacted partially with the water to form those products, so the concentration will have decreased, right? But we're making the assumption that very little of it has actually done or participated in that reaction. So whatever the concentration is initially, we can plug that in because we're lazy. It takes a lot of work to figure out how much it has actually decreased, but it's not a significant amount. Cool. Now we're talking about bases today. This is the new stuff. So we know the general equation for the reaction of a weak base with water. We give it the symbol B. Its conjugate acid formula is BH plus because it's picked up a proton. A base is a proton acceptor. And guess what? For that general equilibrium equation, we can write a corresponding K sub B expression, right? So just products over reactants. What are our products? Well, because it's a base, it's producing hydroxide. So hydroxide is one of the species in the numerator of this equation. And we also have our conjugate acid of the base, so that's given the formula BH plus, also in the numerator. And we're dividing it by that concentration of our reactant, the base. And once again, I know, Annabelle, you're not here, but you sent me a good message yesterday wondering if we can make an assumption with this equation too. We can make the assumption that the concentration of hydroxide and the conjugate acid are present in equal concentrations. That way we can simplify that expression to what you see in the box on the right? We're going to square the concentration of hydroxide ions, and we've done that with that assumption. So the maths is very similar. If you understand where this expression comes from based on the general equation there, you'll understand that, I can work with this equation. It's very similar to what I had to do with weak acids. I'm going to take you through 1 or 2 example problems here before we just try some practice problems. It'll probably be a shorter lesson today because now that we understand how weak acids work, it's very similar today with weak bases. There is one new equation I'm going to introduce though today. There is a new equation, something new coming your way. Oh, and it's actually on the screen.
The base dissociation constant.
That's a thing, but that's not an equation.
KW.
Concentration OH minus equals the square root of the base constant.
That's just a rearranged form of that equation though in the box, right? Taking the square root to get rid of the square above the hydroxide. That's just rearranging that equation. But somewhere in between those two things Ben said, there is a new equation that we have not seen before.
KW over KA.
Yeah, the base constant is equal to the water dissociation constant divided by Ka. That's an important one today. I'll tell you why in a minute.
Got two students that would like to measure the energy in marshmallows.
Okay.
And can they sort of work in a
How are
way
they
to
measuring the
try and
energy
set
of
it up?
marshmallows?
Set them on fire
Okay. Are you supervising it?
eventually.
Okay.
Eventually.
Because I'm just
But-
running this class.
Yes.
Sure.
Yeah.
Yeah. Whatever. That's fine with me if they
I'd
want
like them to try
burn
and
stuff in the
get a
back.
setup going. So if you would just have them some of the back.
Well,
Michelle's class is doing internal. One of us take,
Yeah.
usually they would,
All good. So let me write that larger on the board. KB is equal to KW divided by KA. But often you'll see it written in a different rearranged form. It'll often be written in resources as KW is equal to KA times KB. Do you see how these two equations are the same, but just rearranged? Yeah. KW is equal to KA times KB. I believe that is one of the equations provided to you on the resource sheet in the exam, so I don't think you need to memorize that. Thank you.
You talked to someone off screen before. I'm trying to guess who it was.
Oh, yeah, okay, yeah. Thanks, Annabelle, for confirming that. That's great.
Yeah.
So that's the new equation. I'm glad we don't really need to memorize it, but we're going to work with it today. The reason why we're going to work with it today is because of something pesky question designers like to do. They like to give you the Ka for any question. Even if we're talking about bases, they'll say the Ka of the conjugate acid of that base is such and such. And so they're making you do the work of converting the Ka to the Kb before you can solve a problem dealing with weak bases.
That's rude.
It's rude. It's making you do a little bit of busy work before you actually get to the meat of the problem. So let's do one of these problems here, okay? So we are calculating the pH of ethanamine. Weak base. It's an organic molecule. It's an amine. 2 carbons, ethanamine. Cool. And we know its concentration, or sorry, we don't know its, yeah, we do know its concentration. We're trying to find the pH. And they've given us the pKa because it's a bit of a pain. We eventually need to convert pKa to Kb. So how would I do that? Help me walk through the steps of converting a pKa of 10.6 to a Kb. What do I need to do first?
You have to convert it to Ka, is that it?
Convert it to Ka. So let's convert it to that. So I do, what's the equation for Ka?
Isn't like 10 to the power of
Yeah, 10 to the
negative
negative 10.6.
pKa.
Yeah, 10 to the power of negative pKa. Right? So 10 to the negative 10.6. And then when I get that value, I can convert Ka into Kb. Yeah? So to do that, I know that Kb is equal to the water dissociation constant. So 1 times 10 to the 14 divided by Ka. And I'm just going to plug this in scientific notation. So 10 to the negative 10.6. So if I do that in my calculator, the Kw divided by this Ka, I'll get my base constant. Cool? So I see a few of us are calculating. Hopefully we get similar results. What do you get? 3.98 times 10 to the 24. That's a really big number. It's a weak base. 10 to the minus 4. Okay.
10 to the negative 11.
Maybe you need some brackets or something. Timmick, can you repeat that number?
3.98 times 10 minus 4.
Okay, I'm gonna round it. No, I won't. 3 sig figs. We're good scientists. 3.98 times 10 to the minus 4. Cool. That is our base constant. So it's a weak base, but it's not a particularly weak base. It's kind of an almost stronger weak base. Because 10 to the negative 4 is kind of a larger power for what we normally see. Because we were dealing with some things to the power of negative 12 on things last class when we were talking about weak acids, right? So it's a weak base, but not too bad. So what do we do now? We have the Kb. How do we go about finding the pH of this solution? What do I write out next?
You got KB, right?
I've got KB.
That's really scary.
You need to fucking, sorry. You need to rearrange to find OH.
Rearrange the expression, right? So
Yeah.
it's going to be equal to the hydroxide concentration squared all over the base concentration. I'm just going to put B in for base. All right. So when we rearrange it, we get the formula hydroxide concentration is equal to the square root of Kb times B. Look at that. I haven't plugged anything in yet, but hopefully that makes sense. The square root of the base constant times the base concentration. Cool. Now let's plug things in. So I plug in this value of 3.98 times 10 to the negative 4 for our base constant. Multiply it by the concentration of the base in the problem, right? Now we can finally use that number. So 0.109. Multiply those two together and then take the square root of the whole thing. Cool. And then you'll know the concentration of hydroxide. And from there, it's level 2 stuff, converting a hydroxide concentration into a pH. It does take 1 or 2 more steps, but you know how to convert hydroxide concentration to a pH using some of the equations I have on the screen, right? You could convert it to POH, or you could use the equation that hydroxide is equal to Kw divided by hydronium concentration. And from the hydronium concentration, you can plug it into our pH equation, where you take the negative log of the hydronium concentration. So either way, you'll get the answer in the end. But you can see the method's the same. We've rearranged this expression to solve for hydroxide. And that's about it, really. When we do that, you should find that you get a pH of around 11.8. That's what we're aiming for. 11.8. Cool. So we're going to spend a little bit of time just doing some practice problems. It won't take the whole class by any means because you're getting pretty pro at this. We'll move on to some other stuff for more variety. But give it a go, please, guys, for 20 minutes or so. Page 277 to 278 in the iPads.